Okay, so we want to prove that 1 plus 3 plus 5 plus 7 plus 9 plus 2n minus 1 is equal to n squared using induction. So when you're doing induction, we follow steps. So we have step 1. In step 1, we show that the mathematical statement, this statement here, is true for the smallest n. So in this case, for n is equal to 1. So if you place the left-hand side, we'll pick this part and substitute 1 there. So we're going to have 2, 1 minus 1, which is 2 minus 1, which is 1. Let's see if we get the same on the right-hand side. So the right-hand side, where there's n here, we take 1 and square it. We are getting 1. So we have that the left-hand side is equal to the right-hand side. Hence, the statement is true for n is equal to 1. Then from there, you go to step 2. Step 2 is just an assumption. So you assume that the statement is true for n is equal to k. So what are we assuming? We're assuming that if we get the statement the way it is, and only substitute where there's n, we put k, then we'll get k squared. So all we have done here is, wherever there's n, we have taken k. So k falls in the same set where n was falling. So which set is that? Was there any restriction? No. Okay, it must have been there on top. Okay, so n was an integer, so k is equal to an integer, positive integer. So we've just switched, we've just said n is equal to k. Then step 3 now, that's where now we prove. So we prove that the statement is true for n is equal to k plus 1. So we now prove that it's true for n is equal to k plus 1. If we manage to show that, then since it has worked for n is equal to 1, the smallest n, it has worked for n is equal to k plus 1, then it will automatically work for n is equal to k. That's how the step 2 is being helped. So what have we assumed? I mean, what are we trying to prove here? We're trying to prove that if we go all the way up to k plus, I mean, what is k minus 1? So when you are here, you are dealing with k terms. Now I want to deal with k plus 1 terms. So we'll add the k plus 1 term minus 1. That this is the same as k plus 1 squared. So immediately we write this, we go back and say from here all the way up to here is what we have as our assumption. And it is equal to k squared. So this whole sentence here is equal to k squared. And we have it down. So where there's this whole thing, we'll say by step 2, we have that k squared plus 2k. If we expand here, we have 2k plus 2 minus 1 is equal to k plus 1 squared. So we get this and say k squared plus 2k plus 1 is equal to, so now let's now show that So I've picked the left-hand side and want to show that it is equal to the right-hand side. So k squared plus 2k plus 1, this is the same as k squared plus k plus 1. The factors being 1 and 1, if you multiply them, you get 1. If you add, you get 2. So if you factorize this, we have k plus 1. We also have 1, k plus 1, which becomes k plus 1. Yes? I can't get you clearly. So we have the k plus 1 common, and we remain with a k plus 1. So this is just the same as k plus 1 squared, which is the right-hand side. So step 4 is the conclusion. So you say, since the statement is true for n is equal to 1, for n is equal to k plus 1, then it's true for n is equal to k, and hence true for all n. So I'll repeat. We have the sum. Okay. So we have the sum. So we have the sum 1 plus 3 plus 5 plus 7 plus 9 all the way up plus 2n minus 1 is equal to n squared. In induction, we first show for the smallest n, for the smallest possible n. So the smallest n you can get in positive integers is 1. So we check if it's true for the smallest positive integer, which is 1. And so we substitute the left-hand side, and it's the last part here where it's an equation, or you pick the first number. So it's just 1. In the right-hand side, where there's n, you take 1. So you have 1 squared is equal to 1. So the two are equal. Left-hand side equal to the right-hand side. Hence, the statement is true for n is equal to 1. Step 2, you assume that the statement is true for n is equal to k. So all you do is, where there's n, you take k, so that k remains in the set where n belongs. From there, you go to step 3, where now you prove that the statement is true for n is equal to k plus 1. Now what you have in the statement here, in this statement here, you have that you have n terms. So you have 1, 2, 3, 4, 5, up to the nth term. So in step 2, we have 1, 2, 3, up to the kth term. But this time around, we want n to be k plus 1. So go all the way up to the k plus 1 term. Instead of having k terms, we now have k plus 1 terms. And the number of terms that you have is what you are squaring on the right. So we reached all the way up to k terms, but we want k plus 1. So we added the k plus 1 term, which is this one. And then on the right, where you end is what you bring on the right. So we ended at k plus 1, so we bring k plus 1 squared. When you expand this, you get 2k plus 2 minus 1, which is here, 2k plus 2 minus 1, and 2 minus 1 is just 1. From here, all the way up to here, is what we have in the assumption. And we said it's equal to k squared. So instead of writing this whole long thing, we just go for k squared, because they are equal. If m is equal to n, then where there's n, I can write m. So because k squared is equal to this whole thing, then where there's this whole thing, I'll just write k squared. So I have k squared plus 2k plus 2 minus 1 that is coming from this part is equal to the right hand side. Then now we have k squared plus k plus k plus 1. This was now factorizing it. So from here, it came to k squared plus 2k plus 1. You pick one side to show that it's equal to the other side. That's how we show equality of equations. So you pick this side, you show that it's equal to the other side. So we have picked the left-hand side, k squared plus 2k plus 1, and shown that it's equal to k squared plus k plus k plus 1. When you factor out here, the k will remain with k plus 1, plus you factor out the 1 from this part, we remain with k plus 1. What's common here is k plus 1, and we have k plus 1 remaining, which you can just square, and if you square it, it becomes exactly what we have on the right-hand side. So the two are equal, meaning that the statement is true for n is equal to k plus 1. If it's true for n is equal to 1, for n is equal to k plus 1, then it will be true for n is equal to k, and hence true for all n in the set of positive integers. That's how we show the nice induction here.
Sir,
Yes.
network was. So I was not getting what you're explaining from step 3 here. On step 3, didn't get anything. I think I want an explanation on step 3.
Okay. So on step 3, we have added an extra term. In step 2, we only had k terms. Step 3, we have added the k plus 1 term, so that we don't end at k, but we end at k plus 1. Okay, so everything else remains the way it was, except we are adding a k plus 1. So from there, once you add the k plus 1, then you also do the same on the right. Where you end is what you put on the right. So we have ended at k plus 1, so you put k plus 1 squared there. And then this whole part here is the same as the assumption, which is equal to k squared. So you substitute k squared where there's this whole statement here. And then add the remaining part. This part, you add it here. And then pick one side. So you pick this and factorize, you get this, which gives you that. And then you write it in this form, which is the same as what you have on the right-hand side of step 3, which means the two statements are equal. And that's how we show the equality. Now that we have reminded ourselves, let's go to inequalities. So you go to another example, but this one has an inequality. So prove by induction that the statement the statement for n minus 1 is greater than n squared for n greater or equal to 3 is true. So prove by induction that the statement below is true, and this is a statement that this 4 to the power n minus 1 is greater than n squared, provided n is greater or equal to 3. So our smallest n is 3. So in the proof, step 1 will show that the statement is true for n is equal to 3. That's the smallest n. N is greater or equal to 3. So we can't go back to 1. We've been told that n is greater or equal to 3. So the smallest n is 3. So 4, 3 minus 1 is the same as, this is the same as 4 squared, which is 16. Left hand side. Right hand side. If it was just greater, then you start from 4, because they will tell you where n must belong. So they would say n belongs to maybe integers or natural numbers. So you go to 4. What if it was less? So it can't be less, because we need to know the smallest number. So the right hand side, n, so we're putting 3 squared. This is 9. So we see that 16 is greater than 9. Hence, the statement is true for n is equal to 3. Step 2, we make an assumption. So we assume that the statement is true for n is equal to k. That is, 4k minus 1 is greater than k squared. Then you go to step 3. We prove.
Sir,
Yes.
before we proceed, I'm a bit lost. Can we go back to step 1, the part
Okay.
where we have 9 and 16? What is making it true?
Because 16 is greater than 9.
Oh, we are following the condition
Yes.
where n should be greater than or equal to 3.
Yes.
Okay.
Where 4 to the power n minus 1 should be greater than n squared.
Oh, okay. All right.
So the 4n, which is 3, minus 1, which is 16, is greater than the n squared, which is 9. So
Okay.
the statement is true there. Then now, we prove that the statement is true for n is equal to k plus 1. That is 4k, let me see. That is 4k plus 1. We substitute direct now. Minus 1 should be greater than what? Than k plus 1 squared. That's what we want to show now. Provided k is greater or equal to 3.
Sir.
Yes.
Can we substitute step by step? Direct is a bit confusing. On the right hand side. Oh, sorry, the left hand side.
So on the left hand side, you have just substituted exactly. So where we had n, we now have k plus 1. So instead of writing n here, I've written k plus 1.
Okay.
Yes. So from there, what do we need to do? So let's take it the other side. So we have 4k plus 1 minus 1 should be greater than k plus 1 squared. That's what we want to show. So let's pick the left hand side and see The left-hand side is 4. If we expand this, we'll get k plus 1 minus 1. And this is just 4k. Like that. So 4k, if you multiply 4, then you're going to remain with k minus 1. If the power of k if the power of 4 is k, I can get one of the 4s and multiply it by 4k minus 1. I'll still get 4 to the power k. Is that true? Let's see. This 4 here is 4 to the power 1. I'm multiplying by 4 to the power k minus 1. Because the bases are the same, I can add the power. I'll remain with 4 to the power k. So I can do anything. If I want, I can get a 2 of them. So I say 4 squared multiplied by 4 to the power k minus 2. To now be k minus 2 because I've taken 2 outside. So
can you repeat
okay.
on the
On
slide?
Yes, I can kindly repeat on this one. Confusing.
okay. So we have 4k plus we have 4k plus 1 minus 1. So I've just expanded it to be 4k plus 1 minus 1 direct. So that we get 4k. We have now picked only the left-hand side. So what we have now here is, instead of just having 4k, remember our step 2. Our step 2 is that 4k minus 1 is greater than k squared. So we want to reach to step 2 because that's the one that we use in proving step 3. So we are looking for the k minus 1. So to find the k minus 1, to find the, what do you mean? Repeat from step 3. Okay, that's where we are. We've just written the statement. You prove that the statement is true for n is equal to k plus 1. And then you pick, so I'll pick the left-hand side of 4k plus 1 minus 1, which is just 4k. We want to use step 2, but step 2 has 4k minus 1. So from this 4k, if we multiply by 4, then the power of 4 will reduce by 1. So that if you add back, in case you want to add back, when you add back, you're going to get 4 to the power k, because the powers will add. 1 plus k minus 1 is just k. So the powers will add and you get 4 to the power k, like that. So what you have gotten from step 2 is that this part is greater. Step 2 is saying 4k minus 1 is greater than k squared. So what we have now is this statement here, which is 4k minus 1 is greater than 4k squared. Okay, why? Because we are sure that this is greater than k squared. By step 2, 4 to the power k minus 1 is greater than k squared. And we have 4k to the power, we have 4 to the power k minus 1. So this whole statement is greater than 4k squared. From there now,
So I still don't get, like, on that part for k plus 1 squared. How are we equating it to 4k, or how is it equal to 4k? Because when you expand k plus 1 squared,
no.
like k.
We have gotten the left-hand side of this.
Okay.
Which is this part only. We haven't started talking about this part.
Oh, okay.
Yes, so we're saying the left-hand side is the same as 4 to the power k. Now, if we want to relate the left-hand side with the assumption, then we must have 4k minus 1. So we have try to play a bit of some mathematics here to get 4 to the power k minus 1, which is just multiplying it by 4. But the assumption is saying this part, the 4k minus 1 is greater than k squared. So we can put a greater and replace the 4k minus 1 with k squared. So we have this statement. Now from here,
But by step 2 there, it's 4 power k minus 1, which is greater than k squared. Now, where is this 4 coming from? The one that you put in front here.
this 4,
Yes.
it is this one.
How does it come about?
So this 4 is just this one. Because what is greater,
Okay.
yeah, what's greater is this part, not the 4. So the 4 is being multiplied by this part. So the greater is coming because of the 4 to the power k minus 1. And you can write this. You can write 4 as 2 plus 2. 4 is the same as 2 plus 2. So we can write it as 2k squared plus 2k squared. There is equality.
Okay.
Then 2k squared is going to be greater than 2. It's going to be greater than 2k. Is that true? It must be true that k squared is greater than k. That's what we have used here. So instead of writing k squared, we have just written k. So this has become smaller than the previous one.
Sir, kindly repeat the last part.
So you have 2k squared. Now I want to use a k. So if where there was k squared, I use a k, then it's a must that the one that has k squared is greater than the one that has k. That's what that statement is telling us.
Sir,
Yes?
we have now started the right-hand side, or maybe we're still on the left-hand side.
We are on the left-hand side. We want to arrive at the right-hand side. We won't start it.
No,
We
I
will
was
reach
just
there.
wondering where the tools are coming from.
The tools are coming from looking at where we are going. So we are going to k plus 1 squared, which if you multiply it, you get, if you multiply it, you get what? You get k squared plus 2k plus 1. That's the right-hand side.
Sir, isn't it supposed to be 2k squared plus 2k squared is greater than 2k plus 2k, not 2k squared there?
We can, so the statement is still true, even if we use 2k squared plus 2k. So we have only reduced 1. So we have 2k squared. If where there's k squared, one of these, I put a k, then this becomes greater than the other one. And what we
don't understand.
okay. So for the 4, we said for 4, we said it was 2 plus 2. So for 2, you can as well say it is 1 plus 1. So while there's 2 here, I can put 1 plus 1. Like that. That's just the equality. So I know why you're getting confused. It's just the first time. So you're trying to relate with what you are doing and where the greaters are coming from and the like. So don't worry, we're going to repeat this So let me see if I can finish in the next 1 minute. So we're going to redo it in the next class. So this one becomes greater than, if I remove one of the k squared, then it will be greater than this. But this is what we have as k plus 1 squared, which is the right hand side. Hence, you're concluding now, you're saying step 4. Since the statement is true for n is equal to k plus 1, n is equal to 1, then it's true for n is equal to
n is equal to 3.
K, oh yes, 3. N is equal to K and true for all n. Hey. Okay, I've managed to save. So let's log out and come back quickly.